This is work with my colleague Shishwa Zhang and Professor Arvind. So the first reaction when I talk to someone saying that I'm working on memory model is, when I talk to a computer architect, is to leave them alone. Just pick something and move on. But it is an important question, and especially for RISC V, which cleans up the ISA and so on, you have to even clean up the memory model. So let's see. Why don't we pick up a simple memory model like sequential consistency or TSO? Well, they have simple specifications, both operational specifications and axiomatic specifications, but they have very strict memory ordering requirements. And in order to have an efficient or high-performant implementation of SC and TSO, you have to perform a lot of speculation, and you have to basically track the coherence traffic. Whenever there is an invalidation going on in the coherence protocol, you have to squash the loads, which reads that address. And that's very inefficient. Why not choose something complex like Power or ARM? Well, their memory models are extremely complex. Their operational model exposes a lot of the microarchitectural details. You need to do speculative execution, out-of-order execution, rollbacks, and so on in order to actually understand what the Power or ARM memory model is. And their axiomatic models are also very complex, and they have no bearing to the actual microarchitecture. In fact, if you implement a machine, you have no idea if it conforms to the Power or ARM model in general. So why not something else like RMO, which is supposed to be relaxed memory model, relaxed memory ordering? That's what RMO originally stood for. So there are various issues with these models. The basic issue is it enforces a lot of ordering requirements based on data dependencies and control dependencies. Let me go over this small snippet of a program to show what the real issue is. So the first thread performs two stores separated by a fence called member. That's the fence used in RMO. And the second thread does a bunch of instructions. Let me go over this slowly. So the second thread reads B, which gets the value of 1, which is stored in the first thread. So I show what it gets using this notation. And then based on what it reads, it performs a branch or not. In this case, since it read 1, it will not perform the branch. So there is a control dependency here. So because of the branch not being taken, it goes and executes the next instruction. And the next instruction is a store, which is being read by a load. And then you do some computation with whatever you read based on address C. Basically, you assign the address A to register R3, and then you read from A. According to RMO, you're forced to get the value of 1. But if you execute these 4 instructions speculatively, these are all local operations. So you can effectively get a value of 0 in any typical modern out-of-order processor. So this is why RMO is very strict. So we want to avoid all these complications in the memory model for RISC V. We want to have simple specifications which do not talk about microarchitectural details like out-of-order execution, speculation, and so on. And we want to be able to establish a correspondence between a simple definition and the actual implementation, which involves cache coherence protocols, out-of-order execution, and so on. The definition should not contain that, but the implementation should support all that. Also, we want to be able to be weaker than sequential consistency and TSO for performance reasons in order to achieve high performance using simple implementations, which is the RISC V philosophy. And finally, we want to be able to come up with the right kind of fences to get back the sequential consistent behavior when necessary. So that's our proposal. WMM, which originally stood for weak memory model, but right now it's just an acronym. And the operational specification for WMM is very straightforward. It's similar to the sequential consistency or the TSO specification. Let me go over the ranges of these specifications, sequential consistency, TSO, and PSO, to show where WMM stands. So sequential consistency is very straightforward. You execute instructions instantaneously in order, and if it's a load instruction, you read the memory instantly. If it's a store instruction, you update the underlying memory instantly, so that the next operation, whether it's a load or store, can read the updated value. And TSO is slightly more complicated. You have a store buffer in front of the memory. So any store goes into the store buffer first, and when you dequeue the store, you update the memory instantly. The loads read the store buffer first. If it's not a hit, then it goes and reads the memory. And yeah, it reads the youngest store as opposed to any store from the store buffer. PSO is a variation on TSO where you can dequeue from the store buffer out of order for different addresses. It's a very minor variation. It's not important. WMM is very similar to PSO. The thing shown in red are the diffs. So the difference is there is a new conceptual device called the invalidation buffer, which keeps all the stale values around. So whenever a store is being dequeued from the store buffer to update the memory, you also push the old value sitting in the memory into the invalidation buffer. So that's the stale value which can be read by a future load, by a processor. And when do you clear? So a load can either read the store buffer, the youngest value from the store buffer, and if it's not in the store buffer, it can read the stale value or the invalidation buffer. And if it's not present in either, then it'll go to the memory and read it. And you can throw away a value from the invalidation buffer at any point. So this is basically the operational definition of WMM. There's nothing more to it. And you need to define what fences are in WMM. So the first fence is the acquire-like fence, which we call as a reconcile fence. It basically clears out the invalidation buffer so that you don't read the stale values on a load anymore. And the second fence is like a release fence, which we call as the commit fence. It basically flushes the store buffer so that you don't have any stores sitting locally in your store buffer. Everything goes into the memory. The way it's implemented is you wait till the store buffer is empty before you execute this instruction, and this instruction by itself is a no-op. Okay, what about the axiomatic definition of WMM? That's also very straightforward. So most axiomatic definitions are defined in terms of these reordering rules, which basically constructs a conceptual order called a memory order, which is an order of all the load and store events. Load events meaning when the load gets executed, and store events meaning when the store actually updates the memory. And axiomatic definitions basically give you the reordering rules for these events with respect to the actual program order. So if you have a program, you have a built-in order already, right? So for WMM, loads can overtake loads at any point except if it's for the same address. Stores can overtake stores at any point unless it's for the same address. Loads can overtake stores at any point, even if it's for the same address. That's similar to the TSO definition. And stores can never overtake loads. So that's what this diagram says. And in terms of fences, loads can overtake a commit fences because commit has nothing to do with loads. It just flushes the store buffer. And similarly, reconcile fence, which flushes the invalidation buffer, has nothing to do with the store, so it can overtake it. Okay, so that's the reordering rules. And we need one more constraint on the values which a load reads in order to define a memory model completely. And here it's similar to a TSO. You can either read the latest store for that address in memory order or in program order, whichever is younger in terms of the memory order. So if you want to have a store fence WW, that's what I think RISC V ISA specifies. So you just have to put a commit or a release fence. And if you want a load fence, you put a reconcile. If you want a store load fence, you have to put both commit and reconcile. And load store fence is not necessary because this is not allowed. So we have formally proved that any out-of-order processor which obeys single-threaded correctness, that is, if you execute a one-threaded program, it behaves correctly in some manner. in the most obvious manner of correctness. And if you have such a out of order processor, and if you obey in order commits, you can have out of order commits and still obey single threaded correctness, which is what ARM actually does. But if you have in order commits, and if you have global store atomicity, then that processor, plus if you have some sort of a value prediction for store load values, then that processor actually is exactly equivalent to the WMM definition. So the components shown in green are the ones which you can relax without affecting the equation, meaning if you have an in-order processor instead of an out-of-order processor, it will still stay within WMM. And if you remove value prediction, if you don't do any speculation, then it will still remain within WMM. But if you relax the red ones, for instance, if you don't have in-order commit, it will go outside WMM. Similarly, if you remove global store atomicity, it's going to go outside WMM. And yeah, if you have no single-threaded correctness, it's probably not even worth calling a processor. And so the advantages of this is basically you don't have to squash loads based on the invalidation traffic. Even if you have executed a load earlier and some invalidation traffic comes in the cache coherence protocol, you can just ignore it. So all your checks are going to be local. The loads should not overtake another load or store for the same address. That's the only check you need to do. And a reconcile. And the other thing is you can do some sort of a load address speculation. There is some work going on in this about value prediction. Basically, instead of waiting for a load response and then executing an instruction which depends upon the response from a load, can predict the value which the load will return and then keep executing in the instruction. This affects the memory model in the place where a second load's address depends upon the first load's value. And WMM allows you to execute the second load before actually getting the response from the first load. Okay, so those are the advantages. And the restrictions are instructions should be committed in order, which means stores can never overtake loads, as I had said before. The big advantage of this is it avoids out of thin air values completely. Those familiar with the C++11 models would know this term out of thin air value generation. And let's not go into that, but it's something where you get a value out of thin air without actually storing that particular value anywhere. And you won't have this problem in WMM. So let's look at global store atomicity. So the paragraph here is basically lifted from the RISC V ISA specification version 2.1. The point is they adopt some sort of a release consistency model where they use acquire and release bits, and they permit implementations which don't have global store atomicity. Whereas we are saying you should have global store atomicity. And it's very easy to guarantee global store atomicity in practice, I believe. Any write back cache coherent hierarchy is globally store atomic. If you have write-through caches in the L1 level, they are still globally store atomic, except when you have SMT cores. So just don't do it. And mapping from C++11 memory model to WMM is actually pretty straightforward because the operational semantics of WMM is very straightforward. Whenever you have a load consume or load acquire, you have a corresponding reconcile fence. So you do a load followed by a reconcile. And if you want to get back the SC atomic behaviors, then you have to do some more work. For a load SC, you have to do a commit, reconcile, load, and a reconcile again. And for store SC atomics, you just do a commit and a store. It's actually very easy to derive this or even verify this because the operational model for WMM is very straightforward. And that brings to the end of my talk. So WMM is a very simple memory model specification, which is in line with RISC V's philosophy of keeping everything simple and high performant. That's it. So I would like to point out one more thing. We have a formally verified multi-core implementation of a subset of RISC V ISA using the Coq theorem prover in this hardware formal verification framework called Kami. This is just an advertisement. Yeah.
All right. Question in the back. You can use a center mic too.
Peter Shu Consulting. So you said that this memory model is almost like TSO. Can you say,
except for the invalidation buffer?
Yeah.
part.
So can you say from the programmer's point of view, what would I see exactly the difference?
So you will have to put a reconcile fence whenever you want a load ordering. Whereas TSO never reorders loads. I mean, never lets a load overtake another load.
So how will I have to change my program?
By adding a reconcile fence whenever you want. So if you have a store in one thread and a load in another thread, you have to put a reconcile fence in the second thread. Whereas in TSO, you didn't have to do that. So store A, store B, load A. You need a reconcile fence.
And I wouldn't have had to do that
in TSO.
In TSO or in the same program on x86s either.
x86 implements TSO, yes.
Okay.
But you would have needed that barrier if you were running your code on alpha.
Correct.
That's why I was bringing it back.
Over here,
Rishi or Nikhil from BlueSpec. So the expectation is that from a performance complexity, from an implementation complexity and performance issue, that this will not be any worse. Probably could be better than TSO. And
yes,
right.
You don't have to monitor the invalidation traffic, which clearly makes it less complex than
okay,
TSO.
so I was just going to clarify that, which is that the key to that expectation is that all your decisions are local.
Yes.
And you're not keeping track of invalidation traffic.
Exactly.
It's more global. And the fact that you're doing that is the expectation why it's likely to be easier and simpler and more correct to implement, etc.
Correct.
Anybody else? Come on, don't let him get off the hook that easily. He even got his slides in on time. Actually, case in point, Murali did and Caroline did, our next speaker. Everybody else that went before didn't. They changed them, but. Stefan, you got a question? You're playing with your hair? No?
He's feeling shy. So I have a question. So how does this relate to the transactional memory models that have been proposed, like TSX and, there's a lot of work going on right now.
The hardware transactional memory model.
Yes.
So that kind of preserves sequential consistency at some level, right? And the implementation cost for that is tremendous. You have to basically roll back the entire memory whenever a transaction fails, whereas you don't have to do all that here. But software is easier to code in transactional memory models.
So let's say you have a case where you have two cores and you have different memory channels on one core and some connected to the other core and so on. If there are timeouts that happen, say between loads to different cores and stuff like that, where there is caching involved, and if there's a timeout, would it still work? I mean,
yeah, I mean, timeouts basically clears some sort of a permission bit, right? You give up the permission to read it. That's what the timeouts are for, right?
It says that I wanted a load, I didn't get it from the other machine.
Oh, you're talking about timeouts to avoid deadlocks.
Yeah, timeouts to avoid deadlocks.
So how are they related to this? Yeah, it would work.
It would still
they are orthogonal to
handle at any particular point node wherever you're implementing the WMM.
Right.
It'll still be able to
Yes.
do the write. Okay. And what about in terms of load efficiency?
Load efficiency.
In sense, there are lots of stores, lots of loads happening.
Mhm.
Does it? So the weak model, does it? Is it freer in the sense? Does it allow you to do a lot of bypasses?
Yes, that's what. So you can, given the reordering requirements here, the only reordering which is not allowed is a store cannot overtake a load, and that is something which a typical out-of-order processor would do if it commits instructions in order. So you can always bypass from a earlier store to a load, and you can execute loads out of order. So if it's a miss in the cache currently, you can execute the next load, which may be a hit, and you can keep the value without having to squash it. So it allows all those optimizations. The only thing it doesn't allow is to commit stores out of order, which I think only ARM does.
Okay.
All right. Last question. Okay, good. Very good. Thanks, Murali.